Hello, everyone. We are going to start at slide 73, where we last left off on. I'd like to have my textbook out while I do this with you. So this is the Mesenheimer complex. We talked about this. This is our last slide that we went over yesterday, or the last lecture. Let me get my pen out. So notice with the Mesenheimer, we had the sigma complex, but it had a positive charge, but the Mesenheimer complex has this negative charge that we're able to push around. We have a good leading group. So the substituted phenol product is deprotonated under the basic hydroxide conditions. So acidic workup is necessary to obtain the neutral organic product. So we have to have acidic workup with it. Otherwise, we're not going to be able to get the neutral organic product. And if you want further information on this, on the Mesenheimer complex, please go to page 828. So we're going to go into section 18.14. This goes into elimination addition. It says recall that an SN-AR reaction will not occur if the ring doesn't have a strong electron withdrawing group. So we need an electron withdrawing group, but if very high temperature is used, then a reaction occurs. So you can push these reactions given the circumstances. Since the reaction works even better and doesn't require a higher temperature, but a stronger reagent is used. So here we're using a stronger reagent, and the regiochemical outcome below means this reaction does not proceed through the SN-AR mechanism. So what they did was they're going to label one of these carbons with an isotope, and they do that on the next slide. So they're going to isotopically label this, usually with a carbon-13. So carbon-13 has, 6 protons and 7 neutrons. 6 protons and 7 neutrons. So SNAR stands for nucleophilic aromatic substitution, but we want to see, where is this, how is this all happening? So we're going to label that carbon with a carbon-13. So they're saying this can be due to the formation of a benzene intermediate. Benzyne intermediate, sorry about that, benzyne intermediate, where we have a triple bond right here. It says elimination of the hydrogen chlorine produces a very high energy intermediate called benzyne. This intermediate does not survive long because it is quickly attacked by the nucleophile, producing an addition reaction. Nucleophilic attack can then take place at the position of the isotopic label here, or the other end of the triple bond. I should be saying here or here. So we have 2 places for attack. And they show you the mechanism. So nucleophilic attack by the NH2 can take place at either the carbon or the benzyne, followed by protonation of the other. So we can have attack at either place. If we attack at the carbon-13 position, then we see this right here. If we attack at the other side of the carbon-13, we get this. And the only way we can figure this out is if we have this labeled carbon-13, then we're going to see, otherwise you wouldn't be able to say, oh, this is, where it's attacking at. You wouldn't know which side it was attacking at if it wasn't labeled. So therefore you need to label it with an isotope to figure out where the nucleophilic attack is occurring at. And so this is an elimination addition mechanism. So I'll leave that out. And the next slide goes into how an elimination addition happens. So first we have a proton transfer. So the hydroxide functions as a base and deprotonates the aromatic ring. Then we have the loss of a leaving group. You know, chlorine would be a good leaving group. The leaving group is ejected, generating a benzyne intermediate. Then we have a nucleophilic attack. And after our nucleophilic attack, we can attack at either side of the benzyne group. Then we have a proton transfer, and we get our aromatic ring back. So elimination addition evidence for benzyne. So evidence for the formation of benzyne intermediate comes from a trapping experiment. So they did a small amount of Diels-Alder product is obtained if furane is added. So they added some benzyne with furane and they found the cycloadduct. So this gives evidence that this benzyne does exist for even for a brief moment. So they give a flow chart. The flow chart below can be used to identify the proper substitution mechanism. Are the reagents electrophilic or nucleophilic? And then you go through your progression. Review of reactions. They just have a review of everything we've done. We'll see this in the homework that we do. They talk about this other nucleophilic reactions, nucleophilic aromatic substitution. And these are just other reactions that can occur. They're right on page 834, both of these, page 834. And I just go over this would be a nucleophilic aromatic substitution. We're substituting the bromine for a OH group, an alcohol group. Here we have an elimination addition. So that's it for this chapter. We'll take a brief break. Then we will start up the homework. All right, everyone, we're going to go ahead and resume recording. So we are starting chapter 18 homework. Go to question 1. It says select the statements that are true. There are 3 true statements. On mine, there's 1, 2, 3, 4, 5, 6. I have to select these 2, or these 3. So the first statement that is true is benzene and its derivatives tend to undergo electrophilic aromatic substitution. So electrophilic aromatic substitution. 5, the first word will be addition. There's no other ones that have addition as the first word. So addition reaction with benzene. Benzenes lead to the loss of aromaticity. And the last one is benzene and its derivatives undergo a type of substitution reaction in which a hydrogen atom, there's no other ones that have hydrogen atoms, so you're going to look for this word. It's replaced by a substituent, but the stable aromatic benzene ring is regenerated at the end of the mechanism. So these are the ones that you'll be looking for. Question 2 says add a curved arrow. So we're going to go ahead and add curved arrows. I don't know why it's going like that. So this chlorine, some electrons. We'll add the curved arrow right there. So you have one curved arrow. Step 2 says complete the electrophile used for chlorination. So I'll draw the lone pairs of electrons for this one. This is step 2. So we'll go ahead and negative charge here. You just have to make sure you put all your pairs of electrons around the chlorine. You should be good to go. And then the last part says step 3, which is the electrophilic chlorine atom in the step 2 product. That is going to be my first one. And that's the neutral chlorine bonded to the chlorine. So I'm just going to call it N-chlorine bonded to chlorine. That's your neutral chlorine. We can spell that out, I guess. Neutral chlorine bonded to the chlorine. So that's your answer for 2. We'll go on to 3 now. Question 3 says, we have this benzene, we have nitric acid and H2SO4. This is a nitration of the benzene. Nitration of the benzene, if you want to see the specific mechanism, go to page 798, and I'll show you how this mechanism works. But overall, what we're going to get is this right here. Again, if you want to see the mechanism, please go to page 798. It shows you, it takes you through the steps of how to form the nitronium ion, and then the nucleophilic attack of the nitronium ion to generate the sigma complex, and then the proton transfer. So, I think they do a really good job of showing that mechanism on page 798. And then the name of this will be nitrobenzene. All right, so that's 3. Let me take a look at 4 while you're finishing 3. Okay, so question 4 is kind of along the same lines as question 3. They want to know the intermediates. So it says draw the electrophile. So for the electrophile, we're going to draw the nitronium ion, right? So the electrophile is a nitronium ion. And this can be found again on page 798 of how to form that. So there's your nitronium ion. And then they want you to draw the intermediate. And basically, this is going to get into your sigma complex. So I'm going to just call this I. Oh, we could, I'll delete that. I don't want that there. When we come back, I'm just going to call this I, and I is just stands for intermediate for me. And this is, well, draw that a little better. I wish it would just draw an automatic ring for you here. That'd make this really easy. So we got that. I think that's all they want. They just want the electrophile, which we drew the electrophile, which is the nitronium ion. Remember, it's an electrophile because it wants electrons, right? It's electron loving, has a positive charge here. It wants to take some electrons. You know, we have, well, that's really bad. We have this, and we should just draw the bonds. It wants to eat those electrons up, right? You know, so that's why it's the electrophile. So anyways, I won't draw that because I don't want to confuse students. And that's it for 4. So question 5, this has to do with sulfonation now. So you got to take a step back, I guess. This is on page 795. They show you the, okay, let me see what they want. It says draw curved arrows. So they just want curved arrows here. So we drew our curved arrows, and then that's step 1. Let me see what step 2 wants. Step 2 says add curved arrows to the sigma complex to give the final product. That they use a generic base called B. That's fine. Oh. So we have some base coming in, some generic base. It recreates the aromaticity within the 6-membered ring. And I think that's all they want. Yeah, that's it for 6. So that should be 6. All right, we'll go to question. Oh, this was 5. So let's go to 6. Let me just make sure I'm on the right one. Yeah. So question 6 will be Friedel Crafts. We'll go to that one now. So it says complete the mechanism. Friedel Crafts, that starts on page 800. So if you want to get some more reference to Friedel Crafts and how the mechanism works, go to page 800. It's mechanism 18.6. It says add the curved arrow here. Okay, so we will do that. Yeah, we added the first curved arrow. That's step 1. Now we have to go to step 2. We may have to use another slide, but that's okay. I can generate hundreds of slides, so there's no big deal with that. Just sometimes it wants to do that. I don't know why. There's a positive charge here. This would be a negative charge. So we have that going on. And then it says complete the structures for step 3. I think we can do this on the same slide. We'll just put them over here. I'm just filling the electrons and you're all done. So that's it. So that's steps 1 through 3. All right, let's go to question 7. Question 7, this deals with Friedel-Crafts acylation, which can be found on page 803. So it says consider the reaction. This is an acylation reaction. It says draw the neutral organic product of the reaction. So I'm just going to go ahead and draw the product. If you want to see the mechanism, please go to page 803. This will show you how to get the mechanism for this product right here. So, what we did was we basically added a ketone to this benzene, to the benzene. So that's called a Friedel-Crafts acylation. And question 8 is the same thing, so I'm just going to keep it on the same slide. They give us, let us see, you're basically going to form another ketone, but in this case, we have a tert butyl group with it. So, we have our benzene ring still, right? And then we have our ketone. Coming off of this will be a tert butyl group. So we have that for question 8. A lot of the times the acylation, you'll have this. The products will be just this and then this R group here. So the only thing that's changing is your R group, and here we see it's a methyl group, and here we see it's this tert butyl group. So that's all that's going on right there. Next question is question 9. Question 9, you start with chlorine. So they want the two products. So you have chlorine, and then you're going to add something to it. The big thing to note is, let's see what, so this is question 9. So you're going to have two products here. And both are going to have chlorine, right? If you go to page 811, you're going to see that the chlorine is a ortho and para director. So it's an ortho and para director. So if it's an ortho and para director, you're going to put the bromine here in one case, and you can put the bromine here in the other case. Sorry about that. So it'd be here. So that's where we're going to put our bromine in. So that's question 9. Question 10. It says it wants draw the major resonance form. So we're given this. It wants the major resonance form of 3-chlorophenol. So, at the 3 position, here we have our phenol at the 3-1. Oh, hold on. The ones are a major contributor. So it gives us this. It gives us this, right? And I probably drew this too close. We'll just draw it up like that. You have some electrons here, right? Well, what's going to happen is, you have that positive charge here. You're going to move this here. This will take care of that. So the major resonance form will be, I should draw this a little lower. It'll be this right here. So you're going to draw this. All right, so that should be 10 for you. Let's go on 11. Eleven says, okay, they give you a benzene ring. In your final product, you see a chlorine sulfur group, a sulfonation. So let me think about this. So our reagent one, we'll call them R1. R1 will be chlorine and iron chloride. And that's because the chlorine is an ortho para director. So our intermediate will just be, with chlorine, right? And this is an ortho para director, so then it can put the sulfur group in the para position. Now, if we start with the sulfur group, we'd have to put the chlorine in the meta position, so that's why it doesn't work out the other way around. So then we're going to put the R2 as SO3. H2SO4. That's it. So that should get you where you want to go. And the reason why we start with the chlorine, because the chlorine is an ortho para director. There'd be no way to make this compound putting the sulfur group on first, otherwise we'd have a meta director. So there's reasons for what we do. And the best thing to see which direction stuff goes, just my best advice would be just to review the chapter again. So we have that. So that's 11. Let's go to 12 then. 12, we have the nitration of 1,3-dimethylbenzene. So we know we're gonna have this, right? We're not gonna be able to get rid of the 1 and the 3 position. Now, where do we put the nitrogen on? That's the question. Let me see. So methyl groups are ortho para directing. So it'd be ortho para, and then this one, I could put this in a different color for you. Ortho, because this is ortho here. So what you're going to do is you're going to draw your nitro group here, right? I mean, you could have put it up here. You could have put it here if you wanted to, but I'm just gonna put it in one position. That way I'm not confusing students when they look at the solutions. So either one is fine. So it's wherever you want to put it. But you can only put it where it both says OP. All right. All right, so let's go to 13. So this group right here, this is going to be a meta director. So we're going to be meta directing here on this one. So the only place to put the NO2 then is in the meta position. All right, so that was 13. I'm going to take a look at 14. We can even put it on the same slide. When we have a bromine group, we have an ortho para director. So, okay, we have this bromine group here, and we're going to get two products because this is going to be an ortho I'll just call it an O and a P right here. So we're going to put one chlorine group right here, and then you're going to have another one at the para position. So 15 says, let me see, when orthobromoanisole is treated with sodium amide in ammonia, a reaction preceded by a benzyne intermediate, what two isomeric products are possible? Okay. And the ones that we're going to select are the ortho and the meta. You can think about this. If that base, which is nitrogen, right, takes this, we're going to form that. Really wish they would just be able to have a function where it can draw these for me. Now this would be a good leaving group then. We still have this up here. And then this can attack either here or can attack here. So that's why we're picking the ortho or meta position for that. Now, if it picks here, these electrons that come here then, and this methoxy group can stabilize the carbanion in the ortho position. And we talked about that. Where we talked about that. We talked about that as the Mesenheimer complex. So we're going to pick the ortho position as the most favorable. And it says, why is this product favored? The reason why is the inductively electron withdrawing methoxy group better stabilizes the anion in the ortho position than in the meta position. So there's 4 options. I'm selecting option 4, and it's It's the only one that says the inductively. Look for this keyword. And that should be 15. And we're going to take a 15-minute break here. I think we deserve a break. So let's take a break and we'll come back to question 16. All right, everyone. Hopefully you had a great break. Let's continue on. Let's go to question 16 then. Question 16 says, show how to carry out each transformation in the highest yield possible. Select the appropriate reagents and draw the correct organic product at each step. So that's what we're going to do. Let me see what's going on. Identify reagent 1, R1. Oh. R1 will be, we're going to throw with the HNO3 with the H2SO4. We're going to add the nitro group to it. So, and then we'll draw product 1. So P1 equals this. And we got to draw the formal charge here on the nitrogen. So that will be our P1. P2, we're going to change that nitro group to an amino group. Remember, we did that with the drug synthesis stuff yesterday. We talked about that. So R2, we're going to change the NO2 group to an amino group. So we are going to use we'll draw product 2. I did that. Product 3 is an acylation. Not an acylation. Let me see. Product 4, we're going to add, it's kind of like it, but we're going to, this nitrogen right here, I'll just show this. I'm going to erase it. That nitrogen, it has all that stuff coming off, right? It's going to attack. Let me see. Hold on for a second. Let me see. It has a good leaving group, doesn't it? It's going to come in here, and chlorine is going to be a good leaving group. So that's what's going on there. I just wanted to briefly show what was going on. I'll go ahead and erase it and draw the product. So we'll draw product 3. Back there. That might look like a methyl group coming off, and I don't want that to look like that for someone. So we got that. And then let's see what's going on. Then we're going to add another nitro group. Let me see. So to add the other nitro group, there's a lot going on here, isn't it? So R4. Oh. We had that nitro group. So let's, I have to draw a little bit smaller than what I'm used to. And you're going to want to put this nitro group like that. Trying to work with what I got and getting to the bottom of this page. Okay, so we can always go on to the next slide, but it's nice sometimes to put all this on one slide. And then let's see, what are we doing after that? Then we're converting into the amino group. So to do that, we have to identify reagent 5, and we'll put in this right here. So that's it. So I'll leave that up here. All right, let's go on to question 17. So 17, let's see. We have benzene. Then let's add a chlorine group to it. So to add a chlorine group to it, we're going to add, so this is R1, we'll add Cl2, FeCl3, and then the product P1 will obviously then be just that. Reagent 2 then. With an excellent leaving group. Wow. There we go. Now this is your let me see. This is your Friedel-Crafts acylation. So we got that done. So we formed a ketone group. So we're going to be able to form a ketone group with this. And that's it. So that will get us to where we want, because this is our Friedel-Crafts acylation. And basically we're going to form this ketone group, right, with this R. So this R could be anything coming off. And this is our R group right here, right? This whole thing is our R group. So that might make it a little easier to think about. So we'll do one more, and then we're going to continue on tomorrow. I think we've done a lot. So let's do question 18, and we'll end for the day. So question 18 is draw the product of the reaction shown between propanol chloride and para-methoxynitrobenzene. Include all formal charges. Okay. So this is not the answer, but I'm just going to show you how to get there. So we have this right here. We have our aluminum trichloride. And this is going to move over. Okay. So if that moves over, then what we have is positive. Carbon doesn't like to have a positive charge, so we're going to move this here. And we have this right here. So we have that. So we have to think about this. This is what I was thinking about. We have this right here, right? And we have these compounds that are directing groups. So this is I'm going to put this in, this is an ortho. Let's do para to it. Now let me see. Let me redraw that. I'm just going to put the ketone like this. I'll put an R. Switch colors. Oh, that's not what I wanted to do. I wanted to switch colors. So this group wants to go to the ortho position. The nitro group is meta directing. It's a meta director. But there's already something at the meta position, right? So therefore, it's most likely to occur at the ortho position. So since the nitro group is a meta director, right? And this group right here, this group is a ortho para director. So since there's already something, the nitro group is not going to put something in the meta position. There's already something there. So we need to consider that. So we're going to put it right here. So this is going to be our answer then. Actually, I had that. Oh, I wish. So that wasn't. I was already thinking about where I was at. We should be thinking about like this. And this nitro group is a meta director. So we have two, so we're going to check that right there. So I apologize for that. I was getting ahead of myself. So that's it for question 18. So I will see everyone tomorrow. Hope you have a great day. And if you have any questions, please stay back.